Welcome to the 31st session on operating system and Linux. I'm Manibhushan D'Souza, and in today's class we are going to look at allocations of a frame. So we are going to see what is the minimum number of frames that are required to be allocated to a particular process, and the two allocation algorithms, that is the way in which we can allocate the frames to the process, as well as the difference between the global as well as local allocation scheme. So let's look at the allocations of frame. So what is this problem of allocations of frame? We know that every process requires certain amount of memory in order for it to process. So how much frames should be allocated to a given process? If you allocate a less number of frames, naturally it's going to end up in page fault. If you allocate more number of frames to a process, it will be a waste of resources. So allocations of frame deals with the problem of allocating fixed amount of memory among various processes. So in a multiprocessing environment, there will be many processes which are running. We have to decide how much frames or how many frames should be allocated to individual process. There are different schemes which are available. These include minimum number of frames, allocating algorithm, as well as the global and local allocation scheme. So let's look at the first one, that is the minimum number of frames. Now we know that every process require at least some number of frames in order for it to work properly. So without less number of frames, the process may end up in thrashing. Okay, so we have to decide how much frames, what is the minimum frame that has to be given to a given process. So if it is less than that, then it will create a problem. So you have to see to it that at any given instance of time, the process, a running process, will have these many number of pages. How do you decide on what is the minimum? Now the minimum number of frames depends on the instruction set architecture. So it is based on how the instruction set is developed on a given hardware platform. Now just assume that you are executing a instruction. So let's assume that there is a process and this process executes one instruction. Now before that instruction is completed, maybe you are adding two numbers or adding a number into accumulator or doing a comparison or anything. Now let's say that two operands are required for adding two number. You know very well, to add you require two operand. So add is a binary operator. Now let's assume that one operand is there. So let's to give you in a simple way, so let me assume that you have two numbers here and you are trying to add. Let's assume that one of the number is there in the frame, the other number is not there in the frame. Now this simple instruction, let's say you are trying to add instruction. So this simple instruction of adding two number will not work because one of the number that is required for doing the calculation is not there in the memory. So you have to get them into the memory. Now that's not the end of it, because this instruction is not completed. Whole thing has to be stored. So this whole thing has to be stored back, because remember, when the number is not there, this particular process will be thrown out of the CPU, something else will be scheduled. So all the entire instruction has to be stored in the memory. So even if you don't have one part there, one operand there, the entire thing has to be stored. So at any given instant of time, if you want the process to work, then there must be enough number of frames to hold all the pages that are required for a single instruction. So if the single instruction is referring a few things over there, all the frames related to that single instruction must be there. Otherwise, that single instruction itself will not be executed, and the part of the single instructions will be stored in the memory. So let's consider a simple example. Okay, so let's assume that you have a instruction machine wherein you have only one references. For every instruction there is only one reference. That means there is one instruction. Let me put it here. So there is one instruction like add, subtract, move or other thing, and there is only one operand. So instruction part has to be there in one frame, and the operand part has to be there in one frame. So that means to say that for this simplest architecture wherein you have one instruction and one operand, you need two memory reference. So that's required in this case. For a very simple operation like this, you need two references. Now let's assume that there is one level of indirection. So what's the meaning of saying one level of indirection? Suppose you are trying to refer to a location, okay, and the instruction says refer here. It goes to one of the page. From one of the page you have the one of page contains only the index to the actual data. So the actual data is there in some other page. So let's say you have some actual data, say 60. So it says give me the value of x. So it comes here, and the x says it's a pointer to some other location. That means you are not directly getting the value, you are getting one indirection. So in this case, how many references are required? One page is required for the instruction, two pages are required for the memory access, that is the operand. So that means altogether you need 3 pages to be very precise. So that means to say that per instruction you require 3 frames per process. Now what if there are only 2 frames are there? Suppose if you allot only 2 frames to this, in that case, suppose say you have the instruction which have one indirection, you have the instruction, you have the operand. Now instruction you have allotted one page, and operand you have allotted one page. However, what is the problem with the operand? Operand is a indirection to some other page. So what happens whenever this instruction is executed, there will be a page fault, because this page the actual page, this is an index to the other page, this actual page will not be available in the memory. Now the worst case scenario is where there are n number of indirection. What is the meaning of saying n number of indirection? You have one index onto this will index onto some other page, that will indexed onto some other page, and finally you get it. So that means many pages will be there in the memory. So what I mean to say that is there is a very difficult it's a very difficult task as to decide how many minimum number of pages are required. Okay, by the way, we can always decide what will be the maximum number of frames that can be allotted to a given process. If I ask you that question, think about this. What will be the maximum number of frames that you will allocate to a given process? So can you decide on that answer? So maximum number of frames will be always the total number of memory. You can't give more than the memory. Okay, if your RAM is 1 GB, you cannot allocate more than 1 GB, because your physical capacity itself is 1 GB. Hope you get that thing. So there is a confusion between what is the minimum, but there is a definite answer what is the maximum. Maximum is the whatever memory that is available, entire thing can be given to a process. Now we have to decide between them whether it is the bare minimum, which is not very accurate, but bare minimum, or the maximum. In between we have to make a choice. One of the simplest way of allocation is the equal allocation. So what is this equal allocation is, every process is given equal number of frames. So in other words, I distribute and say, okay, 5 frames to you, 5 frames to you, 5 frames to you. So I give all the process, I give equal number of frames. Okay, so how do I decide about that? So first of all, I check how many processes are there with me. Suppose if I have five, suppose say in my machine at a given instance of time, if I have seven processes which are running, seven programs are running, and I have 50 frames with me. So what I will do, I will divide it by 7. Remember, I cannot give 1.5 frames. I will give an integer number of frames to them. Okay, so that means to say that I will give equal number of frames. So in order to avoid the confusion, so I'll give you a better example, and that is, say if I have 20 number of frames in my machine, and if I have 5 program which are working or processor, then every process will get 4. So if there are m number of frames and n process are running, you will give m by n integer part of it, definitely. So every process will get equal number of frames. Okay, now suppose once for example in the previous case, when I divided it with say 50 by 7, now what happens is you get 7 for everybody, so that will be 49. So 49 frames will be there, and leftover is 1. Then I can give it to somebody else, or I can put it as a buffer. One, I'll keep it as a buffer. So it's up to you how you keep it. So remaining frames which cannot be allocated, because you know very well, when you divide two numbers you get a fractions. I cannot give fraction of a frame to a process. Then either entire frame has to be given, or I can't give any frames. So whatever that is left over, I can put it in a pool, and later I can utilize it. Okay, so the problem with this is we have to, sometime it may so happen that when we give equal number of frames to all of them, we may be over generous. What is the meaning of saying over generous is we may give them more than the frames that they actually require. So if it's like if I have 100 frames, and if I have 5 processors, so if I have 100 frames, let me show it here. So if I have 100, and if I have 5 programs or 5 processes are running, then everybody will get 20, isn't it? So it is as simple as that. But the problem is, some of them may actually don't require 20 frames at all. Okay. They may be happy, their entire program itself may be within 10 frames. So other 10 is waste. So it is like over generous. You gave more than what is required. So you went for equality. Equality means you are not considering whether they really require it or not. You simply give them the frame. So let's look at a simple example. Suppose if every frame is of 1 KB size. So every frame is of 1 KB size, and you have 2 processes. One requires only 10 KB. The other requires 127 KB memory, and there are 62 frames which are free. Okay, so you know very well, because 62 frames are there, you divide it by 2 processes. Remember, one is 10 KB, other one is 127 KB. You divide it by 2, so you get 31 frames. So give 31 frames to the first process and 31 frames to the second process. Now you may say that I have given equally, I have distributed equally. But what is the problem over here is, look at this one. This if every frame is of 1 KB size, that means out of 32, it will only use 10 frames, that is 10 KB. Remaining 21 frames are wasted. It will not touch them at all, because that much memory itself is not required for the process. Entire program can work within 10 KB. So instead of simply giving it, you should have given it to the other process over here. So when you give equal frames, it may not be a great idea. So what do? You change the notion and you say that we will give proportionately. How much they need, we will give. So according to their size requirement, we will give them. Suppose if a process P requires a frame of size S, so you decide how many processes are there. For every PI process, what is the size? So if there are 5 processes are there, you ask all the 5 processors. You ask the first process, okay, what is your requirement? The process may say, okay, I need 20 frames. Okay, you call the second process. Okay, second process, come here. What is your requirement? That it may say, I need 25 frames. Okay, you call the third one. Come here. What is your requirement? Okay, so for every PI process, you get the requirement. What is the size? And you sum total them. So this must be the total size that is required. Yes, is the total size for all the process. So every process require a size of Si. For all the process, it will be summation of that. Okay. So for example, first process may say I need 20, second process may say I need 25, third process may I need 4, fourth process may I need 67, and the next may say 90, and so on. You sum all of them, this is the total requirement. So there are 1, 2, 3, 4, 5 processes are there. So you have 5 processes, all of them require this much of memory. Yeah, simple as that. So now look at what is the total capacity you have. So if your total capacity is M, then proportionately you give them. So what is the requirement for Si, for the process Si, divided by the total number? You will get the fraction, multiply it with the M frames. That is what you get it. So for example, if the first process requires 20 frames, and if you sum all of them, all the process, if they require 100, and if you have 50 frames with you, then what will be the answer? Okay, so you do this one, multiply it, whatever answer you get, that much you give it to the process P1. Similarly, you give it to the process P2, and so on and so forth. Okay. Definitely, as you know, when you divide, you get the fractions, and you know very well, the fractions must be converted into integer in such a way that total allocation does not go beyond the total size of the memory available size. So just to give you an example, so the same example, we had 62 frames with us, and there are one process that require 10 pages, other require 27 pages. Okay, so you take sum this one, it is 137 total. So for the first page, 130 10 by 137 into 62, that is a total number of frames. This is Si. So if you take this is Si divided by S, okay, into total number M. So total number of frames is 10 plus 27, that is 137. 10 is one requirement, 10 by 137 into what is available, 62, and you get that. So for one process you give 4 frames, the other process you give 57 pages. So this way, okay, you share the frames as needed by the processor rather than generously give additional number of frames. Okay, whether it is equal or whether it is proportional. Now the number of frames that are given for a given process varies depending upon the number of multi-programmings. Remember, when the number of multi-programming increases, when the level of multi-programming increases, the frames that are given to the process may decrease. So for example, at this instance of time, there are 5 programs running. Maybe after t1 second, if 7 processes are running, then naturally the number of frames that were allotted here will change, because now additional 2 processes are there. Remember, you have the memory is same, you can't change the memory. So when it was 5 processes, you might have given sufficiently good amount of memory, but when the number is greater, when it is 7, everybody may get slightly lower frames. Okay, and again if it is reduced to 4, they may get a slightly better frame. So depending upon the number of programs which are running, that is the level of multi-programming, either you may increase the frames or you may decrease the number of frames that are given to a particular process. Okay, now the next question that will come to our mind is about the priority. Now you know very well in the multi-programming environment, some of them have a higher priority. So it is as simple as that. So even you are driving on a road, even though you have your new bike or new car or anything, if the ambulance comes, you have to give away. Okay, if the chief minister's car passes by, it is better you park your vehicle to the bring it to the left side and park it on the left hand side, because you don't want to compete with the chief minister's car. Okay, why? Because chief minister car is has a higher priority, ambulance has a higher priority, if the fire engine comes, it has a higher priority. So in the same way, when we talk about the processors, there are many processors which are required by the operating system itself. They are called as kernel level processor. They have the higher priority than the lower end, that is our applications that we are running. Now if you keep them waiting, the higher priority process waiting, then the end result may be disastrous. So what I want to say here is, if you give proportionately also, if you give, or if you equally distribute it, you are not giving preference to the high priority. So what do you mean by saying that is, if you have a high priority process, it is better you give them more frames so that they can complete it much faster. Okay, they can increase their speed of execution. Otherwise they will end up in page fault, and they may end up in thrashing and so on and so forth, which is an adverse effect and which you don't want to happen. So in that case, what you can do is, a higher priority process can be given extra memory. Okay, so in your proportionate algorithm, what you can do is, proportionately you can give some priority. You can combine the size along with the priority, some factor, priority factor, and based on that you can allocate the frames. Now let's look at the page replacement algorithm. Now allocation also depends on the page replacement algorithm. Now remember, you are giving the frames. So when the process comes and you say, okay, you take 5 frames and go. When the other process comes, okay, you take 5 frames and go. So what happens is, in the beginning stage, it is all good, everybody is a very good person. So you give 5 frames to them, one process. Okay, the process is very happy, okay, thank you, and it says it will thank you and it will go. Next process also you give, and so on. You allocate all the entire memory. Now one of the program is executing, suddenly it will generate a page fault and say that, no, I don't have this page, get me this page. Even though you allotted them the fine number of frames or n number of frames, but it says that I want extra frames. So it is it's a general thing. When the program is running, it may suddenly come back to you and say that one page I require, urgently one page is required, because some reference has to be done on that page. So when a new page is brought in, okay, when a new page is brought in, it will have to knock out an existing frame, because you have already allotted all the memory. Okay, now the problem comes is, which one are you going to pull out? So that is the question, that is called as page replacement. When a new page comes, one of them has to be replaced. One of the old frames which are here has to be replaced with the new page that is arriving. Now which one are you going to select? There are two options are there, one is global, other one is the local. Okay, so the two classifications are there. In the global, what you are doing is, the global way of doing it is, okay, one of the process says I want a frame, so you just find a victim from this one, regardless of whether that frame belong to the current process or that process belong to some other process. You don't bother about it. So one victim frame, you take it, it may be used by some other process, but you don't care about it. You wanted to get one page into the memory, so you just pull them in, knock out one of the process, one of the frames, even if it is not, it does not belong to this particular page, it belongs to that different process. So this particular frame is used by P2, and P1 said I want a page. So what the operating system will do is, it will knock out one of the frames which belong to other process. Okay, that is called as a global replacement. It may again, it may knock out the the frames that may be belonging to P1 also. It is not that it will always knock out the other processes frame. it is up to the operating system. So you are giving it a free hit, so you can hit anything. You can replace your own frames, or you can replace somebody else's frame. So such a replacement algorithms are called as a global replacement. What about the local replacement? Local replacement is very, very simple. So in the local replacement, if p1 says I want one frame, then only those frames that are belonging to the p1 are knocked out. The other processes frames are not touched. Okay, so as simple as that. So it is only the local frames of that process are that are being replaced, but not the other way around. So there are two different ways in which the page replacement can be done. Now again we come to the problem of high priority and low priority. So what to do in case of high priority and low priority? Now, when you have the high priority process, you can go for a global replacement. What is the meaning of saying global replacement? Remember, whenever there is a high priority process, we want that process to be completed because it has a higher priority. Now, if you replace its own frames, okay, the high priority is its own frame, that is a local replacement, then it may again page fault. So it is better you find a victim from the other process which are low priority process and knock them out. So it is simple as that. No, when the rich people want something, the poor people have to give up. So it's not fair, but it is generally it is being followed. So when you have the higher priority process which is running, it when it requires frame, you just find the victim of a low priority, knock it out and give it. Is it fair? It is actually fair because you are giving priority to the one process. If you don't give the priority, if everybody is equal like a communist, then everybody has the same rights. Now here it is a democracy, so some people have actually the ability to do that. So you knock out the low priority and keep the the higher priority frames there and complete it. Now your intention here is to complete the higher priority process. It is not that finding a victim there. If the higher priority processes are not completed, then it will have an adverse effect on the system. Look at the thing. There may be some operating system routines which are running, which is very, very essential. Now, if you make it waiting, the end result would be operating system itself may become unstable. Then onwards, nothing is going to work. Okay. See, just because you find a pretty on low priority and you say that no, I'm not going to touch them, it's not a good thing. But it's a great idea that you give equal priority to everybody. But what is low priority is something that can be overridden. Like you are playing a game, okay, and suddenly your disk has some problem. Okay, it is better to correct that problem rather than allowing you to play games and everything will get stuck and you will have to reboot the system altogether. So it is better. You are playing your Angry Bird can wait, but the disk problem cannot wait because it will create a unwanted problem there. So when you think about the global priority, now high priority, it is better we give extra priority. So higher priority will replace the lower priority. Now what about the local replacement? They do not venture into that, okay, because they are a very goody kind of situation wherein I don't disturb the others, I don't expect others to come and disturb me. So very great idea, but in the prioritized world it may not work. However, there is one problem with the global replacement algorithm is the global replacement, whenever you use that, a process cannot control its own page fault. So what do I mean by saying a process cannot control its own page fault? Remember, when does a page fault occur? Suppose if you have a process here, when does a page fault occur? When your process does not have a frame in the memory, you generate a page fault. So that's simple as that. Okay, you are running a process and your process does not have one page. It will go to an operating system and says, I want that page, you get it. That is a page fault. Now what happens in this case is the operating system gave you enough number of frames for you to work. But what happened is a high priority process came in. So high priority process came in and it knocked out the frames which were given to you, because your program was, let's assume that it's a low priority. Now there is no fault in your program. Your program had all the frames, but somebody else came and removed your frames. So is it your fault? It is not your fault. It is somebody else who created a problem to you. So you are look at your process. Your process cannot control its own page fault. It is generating page fault not because it has a problem. It is generating page fault because somebody has robbed its pages. Okay, a high priority process came and robbed its pages. That is why it is generating a page fault. So when you have the global replacement algorithm, what happens is a process doesn't know when it's going to end up in trouble, because anybody can come and take its pages. Anybody can come and steal its pages and take it away. Why? Who is this anybody? Higher priority process. The higher priority process will look at the lower priority and they will, okay, laugh at it, and I'm going to take your frames now. You just take one and go. And your poor process, it will have to cry. Okay, so there is no way it can control its own frames. What about the low priority? Low priority, such a problem does not occur. Look at a simple scenario. Now when you have when a process cannot control its own page fault, what is going to happen is the performance of the program varies differently at a different instance of time. For example, your program may take 5 minutes, just to give you an example, 5 minutes for completion today. Tomorrow it may take 1 hour. Why it took 1 hour, you may ask. Okay, yesterday it completed in 5 minutes, now why it is tomorrow? Why? What happened is there are many high priority process came in somehow, because you don't know, there are things are changing and they are simply knocking out its pages. So what happens is its execution time is different in different days. So you cannot say that my program is going to end in 5 minutes. Today it may end up in 5 minutes. Tomorrow, because of many higher priority process which are running, we are talking about multi-programming environment wherein more than one program can be there. So because many processes are running, what will happen is they are knocking out your pages. So end result is you are losing your frames, and whenever there is a page fault, you will have to wait for input output operations. So that adds extra time on your processing. So you cannot guarantee that a process will complete in 5 minutes or 10 minutes or 1 second or 10 seconds, because it is not able to control its own page fault. Okay, whereas in local, such a thing does not happen, because you know very well in local everybody is good. So you know, some if you go to some places where you have this villas and other, everybody is a good person. You go to apartments, every person is a gentleman there. Okay, so such a kind, so this that's called as a local replacement. Everybody is happy with themselves, they don't go and disturb the others come and don't disturb them. So that's well and good. However, one thing you must understand is even though global replacement has a lot of problem, it is the one that is preferred because it gives a higher throughput. It's able to complete the programs much better. No, you know, if everybody is good, what happens is they are always lazy, slow, they are not doing anything. See, if you, it's like in your life also, if there is no excitement, that means you are not doing anything. Okay, so if you are doing something, then only all the problems will come. If you simply sit at home, nothing will come. Okay, same way these local allocations, what they are doing is they are only happy with what is given. They are not trying to explore out. Whereas this global, they are exploring, they are high exploring, they go and steal the pages of others and then they complete their work. So you start a process, a high priority process, it will go rob all the pages from the others and immediately it will complete. So that's a good thing. So when it completes, its number of programs that are completed increases, because every process quickly completes it. If the pages is not there, it will go rob somebody else's pages and it will complete it. So in a given amount of time, more number of processes can be completed in a global allocation. That is why global allocation has a higher throughput. And we need some in any system, we need a higher throughput. We want more programs, more process to be completed in a given amount of time. That's why we are using computers. So naturally, global setup is considered or a global allocation is considered. That's all for today. If this was interesting and if you want to know more about it, please refer the Galvin's book on the operating system. Thank you for your interest. We will meet again in the next class.